Welcome back to this NPTEL online certification course of molecular rearrangement and reactive intermediates. In the last couple of classes, I was talking about organoboron compounds. So I talk about very important reaction like hydroboration, oxidation. They are enantioselectivity and they are the stereoselectivity. Also, I talk about the Sujui coupling reaction in the last class, and the allyl boron compounds. The reaction with aldehydes. And then also I think I talk about the other important reaction is the Hayashi coupling using organoboron compounds, the 1,4 addition reaction, and also about the boronotic reaction. In the today's class, I am going to talk about there are a lot of reaction with organoboron compounds which goes via a 1,2 metallate rearrangement. We call it as a 1,2 migration. We generally see a group from the boron going to migrate to the next carbon. Okay. So we are going to start about some of these reaction, okay, and also I am going to talk about other reaction like beta-cis reaction and some of the other important chemistry using organoboron. So let's try to understand what is this 1,2 migration I was talking about, or what is this 1,2 metallate rearrangement, and then I am going to talk about different types of them, different types of 1,2 migration. Of course, this is a huge topic. I am just going to give you a brief idea about it. Then the Madison homologation, one of the I think named reaction for 1,2 migration reaction, and you still find some question coming in the competitive exam from that. And then of course one of the example from the Agarwal group who have contributed a lot in this area. And then the G4 olefination and the beta-cis reaction. So let's try to understand first what is this 1,2 migration I am talking about. I think if you remember when I was talking about this hydroboration oxidation chemistry, first thing we understand there is a chain addition of the boron and hydrogen to the olefin, and then after the consuming 3 different olefin, 3 equivalent of olefin, you end up making to this trialkyl boron compounds. But then once you treat with H2 to an NaOH, you generate this OH minus, this hydroperoxide anion. So that is going to attack to the empty orbital of the boron to form this boronate complex. So once this boronate complex formed, you have learned in the previous slide that this R group going to migrate from boron to the oxygen because this OH acting as a leaving group. So what is the concept you are learning here, that if you have a boron and having a R group, okay, having some sort of a boron 8 species, and then if you have a X group here and there is a leaving group here. So that means if you have a leaving group here, then the important thing is now this R can give electron density to the corresponding sigma star orbital of this XL leaving group bond. If that is happening, then this 1,2 shift is happening to get to the corresponding product. So that's how you come here in this step first, and then after there will be 2 equivalent of another hydroperoxide going to come and form all the way to this BOR3, and that is going to hydrolyze to the corresponding alcohol. So the important thing is here in this particular tangent state, you have to understand there is a anti-periplanar relationship between these groups. So then you can see they are literally in a parallel. You can think about these two are in a parallel, and these are so the leaving group and these are actually anti, because you can see from here this is the group which is giving electron density to the sigma star, and this is the bond which is getting flipped. Okay. So this anti-periplanar relationship is very important when there is a 1,2 shift is happening. I think I talk about that in case of carbocation chemistry when I talk about pinnacle rearrangement. If you remember, then when this 1,2 migration is happening, every cases this the periplanar arrangement is very important for this 1,2 migration to take place. So you have learned about oxygen in case of the hydroboration, but further this chemistry was developed and people started using carbon instead of oxygen there. Correct. Now if you have a carbon here instead of oxygen and you have a leaving group, then very similarly the boron from the group from the boron will migrate from the boron to the carbon to get to the corresponding product. But now the reaction depends on the electron density of the migrating group. Okay, that is the guiding factor. Then the lesser the steric hindrance around the migrating terminus. So what is the steric hindrance around the migrating terminus? So that can also hinder some of these migrations, and most importantly the anti-conformation among the migration group. So if you are not able to achieve that anti-conformation, it will be very difficult for this migration to happen. The rate will be much slower. Now there are several different types. Again, this could be a we can talk about an entire semester about this 1,2 migration using the boron, and our group are also working in this area. So there are a couple of different types, but I am just going to bring you two important type here. That first is here, that if you have a carbon here which have a leaving group. So we are talking about the carbon which attached to the B minus having a leaving group here, then this can participate in a 1,2 migration. This is a type 1. Now there could be a type 2, type 3 and type 4, but I am going to just restrict you to the type 2. That now if you have a olefin here, so now you have a vinyl boron compounds, but the boron is in a boronate, correct. So now if you can activate this double bond with a electrophile, now if that is going to generate some sort of a delta positive charge. So that is another thing. If you generate the carbon attached with the boron in a boronate complex, so what I am talking here, that if you have these groups here and you have a carbon here, where if you can able to generate some sort of a delta plus character. So that could be, if you have a leaving group, then of course once the leaving group is getting out, you are generating a delta plus character. If you have a olefin here and you are giving electron density to the electrophile, you can generate some sort of a delta plus character here. So that delta plus character is going to allow you to this migration to happen. Also there are example where you can able to I think you can take a radical here. You guys have already learned the radical chemistry. Now if you can have a radical here which can add to this double bond, that will be generating a radical next to this boron carbon, and now that radical it can become a carbocation. If someone can take the radical from there and become a carbocation, that can also allow this 1,2 migration from the boron to the carbon to take place. Original, the achiral version from the Madison group, if you treat the sodium iodide and the acetone, what is happening? You are forming this compound very fast, and one of the explanation for there, that the I minus is attacking the boron, forming the boronate complex, and then the I actually moved from the boron to the bromide to get to this compound with a very good yield. So it is not like a simple SN2 reaction here, it is actually some sort of a reaction with the boron first to make the B minus, and then a migration from the boron to the carbon. Okay. So now you can see it could be, if you have a something like that. So we are talking about some sort of a alpha halo organoboron compound. So we are talking about alpha halo organoboron compound. So it could be the boric esters. You are seeing these are boric esters here. So if you treat it in a Grignard region, again so Grignard region is R minus, that is going to attack to the boron to form this boron 8. Now that will allow this R to migrate from this boron to eliminate this, to get rid of this the leaving group which is the bromine, to get to the corresponding product after the 1,2 migration. And there are several different examples for this. Now the next example here, that previously we have learned, if you have a alpha halo bromo alpha halo organoboron compound, what about if you can bring some organolithium? So your lithium has a corresponding carbon halogen bond, that means that can also act as a leaving group. That means your organolithium has this leaving group, then that can add to the boron to form this boronate complex first. Now the R group from boron can migrate here to get rid of the chlorine to form this corresponding alpha halo compound. So now you are synthesizing it. Okay. Now you are synthesizing the corresponding alpha halo compound. Again, if you take this compound and take another equivalent of RMgX, correct, maybe in R dot, you can replace this chlorine by R dot. Okay. That means you can do simultaneously two reactions. And some of these example here, you can make different type of this alpha halo boron compounds from this reaction. Again, I think one thing is important in the previous slide, I think I should mention you, we are going a reaction at minus temperature, such a low temperature for this reaction. Okay. Because you can understand this is a very reactive species, because you have a lithium with a carbon halogen bonds, correct. So that is a very important thing, and in this reaction, so that the reaction you want only that it can bind with the boron, it cannot do some other reaction. So that's why you want to make sure the reaction is very low temperature for getting the chemoselectivity right. There is another reaction. Now the idea is, okay, we have learned this 1,2 migration for this corresponding dichloro compound. How about getting this corresponding alpha halo organoboron compound enantioselective selective? For that, you can able to the Madison actually take this idea that if you take pioneer diol and if you take a phenyl boronic acid, then you can make this corresponding boronic esters here. Now if you can see, now you have a chiral group attached here, so that means the boron esters become chiral, very similar to, you see, we have talked about the chiral boron in case of the allylation reaction, correct, using allyl boron compound. So if you treat with the very similar lithium CaCl2 in presence of diethyl ether at minus 70 Celsius, now you can able to make this center chiral, okay, after the 1,2 migration. Okay, we are going to talk about a very important thing in this reaction to improve the enantioselectivity. At the beginning, this enantioselectivity was not great. What they find out after several screening, that if you use a zinc chloride in this reaction as additives, then you can improve the enantioselectivity to very high enantioselectivity. So what is the role of zinc chloride here? One of the problem, if you try to understand in this reaction, so you can see, with and without. So you can see the difference in E's, okay, and also the yield. So there is a great difference of yield and E. Okay, we try to understand what is happening here, because you can think about in this reaction. Let's try to understand the two different tangent state here. That once you have this, so this is a prochiral center. You can think about, there is a 2 chlorine. Now you want to make this prochiral center, so that means there is a 2 chlorine. You can see one is here up, one is down, correct? One is, so this is a up, this is a down. So if you think about these 2 different chlorine, each of them going to migrate for 1,2 migration, going to eliminate, going to make a new chiral center there. So that means if you can able to control this diastereomeric tangent state, that means if you can make some sort of a chelation control, then you can able to get to 2 different type of tangent state, where one could be higher energy than other, and in that way that chelation model can allow you get to one of the enantiomer with a very high enantioselectivity. So you can see one of the tangent state here, you can see these chlorines are close enough for that's why there is a repulsion here, okay. In other cases that is not happening because they are interacting with this hydrogen. So now you can see now you can able to differentiate between this prochiral chlorine. So the 1,2 migration can happen only to eliminate this particular carbon chlorine bond, okay, to get to the corresponding product with high enantioselectivity. Here there is an example. If you use a C2 symmetric boronic esters, if you use C2 symmetric chiral boronic esters and this corresponding lithium, it can generate this corresponding boronate complex here. And now if you treat with the zinc chloride here, so now you can see now you have used a chiral diols. So these are the diols which are chiral. So you synthesize them and then you make a chiral boronic esters, and then if you treat with this corresponding lithium, it forms this boronate complex. And now if you treat with the zinc chloride in the room temperature, again these are the things. You can see there are 2 different tangents going to happen. One cases you can see there will be, if you have isopropyl group here, they can interact with the chlorine as well. So this type of interaction now going to differentiate between 2 different tangent states. So that can allow the reaction to go through this particular tangent state to get to this corresponding alpha halo boronic ester with a very good yield and very good EE. Then later the Agarwal group have done a lot of contribution in this area. They initially started with this type of acting the sulfur as a leaving group here. Again you can see this is again this is already have a chiral auxiliary here. You are generating again a minus plus, so the minus can add to the boron, triethyl boron, to make the boronate species. Now the ethyl group can migrate and the sulfur can act as a sulfur can eliminate to form the corresponding the chiral, the dialkyl boron compounds, the trialkyl boron compounds, which can be oxidized to the corresponding alcohol using the 1,2 migration chemistry. And their group also find out, so this is mostly, you can see this is a mostly substrate control. You are bringing this corresponding in the minus, which is chiral, which is adding to the trialkyl boron, and there are something called a reagent control. That means you now start with the chiral boron compounds. So you either start with the chiral boron compounds or you start with the achiral boron compounds. You have 2 options here. Now in these cases we are talking about, I think, generation of a chiral lithium. So I already talked about that if you use a spartine, I think I already talked about in the organolithium chemistry that this is the OCB. So depending on, so there is isopropyl group here. So now you are using spartine to come here. I think as I mentioned that if you have a lithium which is getting stabilized here through the chelation with the oxygen, and you have this chiral spartine which is making a complex with the lithium. That is allowing you to the abstracting this proton from here to generate a chiral lithium here. And that chiral lithium, once you treat with the organoboron compounds, what is going to happen? If you take this and if you use the organoboron compound, this is going to add here, correct? So this is a case you have started with, that if you take this type of organoboron compounds with this lithium that can participate in a 1,2 migration, okay. Once you have a chiral lithium, you can, if you take a suppose a phenylbutene also, let's take some phenyl boronic esters, then what are you going to make? You're going to make, so now you have already the lithium is chiral, so I'm just trying to show you that, okay, so that means if your lithium is chiral, then this is the center already chiral, you have this phenyl here, and this OCB can act as a leaving group, okay, and you have a R. So now this phenyl or the R group can come here to get rid of this OCB to get to this product. So now you end up making a chiral boron with a phenyl here, okay. Or you can use just a simple lithium, not the with spartine, using timeda you can make this simple lithium using sec-butyl lithium, and now you can use a chiral boron compound. So if you use a chiral boron compound, you don't have to use another things chiral, you can use that, but of course if you use that, you can able to make all the different combination what you want. Of course, that is the possibility to make a diastereomeric cases, because you have a 2 chiral center. Now if you want to control the 2 chiral center, you can generate a chirality from the corresponding OCB, and you can bring the chiral boronic ester. So that way you can able to control these 2 chiral center, you can able to get all the different the enantiomers. So you will be able to get all the different diastereomeric pair and also the enantiomers. These 4 different compounds, if you know you have 2 chiral center, you can end up getting these 4 compounds. There will be 2 of them will be enantiomeric pair, and all these 4 compounds can be isolated using this strategy. Again, the other things I am going to talk about, that how you activate the double bond here using an electrophile. So that can be done using an electrophile like iodine, and that is going to introduce you to the Juifer olefination that was discovered in 1967 by Juifer and co-worker. Then if you take a if you take alkyne, and if you go for a the hydroboration, and if you treat with iodine and in presence of a base, then you can end up forming this corresponding Z selective olefin. So we're going to come back to that. Okay, so I think in this reaction what is happening, I think this will be R dashed will be here. I think this will be a Z olefin here. So what is happening at the beginning, if you take this corresponding vinyl boron compounds, okay, and treat with iodine and NaOH, you end up making the corresponding Z olefin. Okay. And now if you treat with the bromine and NaOH, you got to the corresponding vinyl bromide. So there is 2 things happening. I think one of the important thing is when you have NaOH, I think we have to understand the corresponding mechanism how this reaction is happening here. Okay. So in the next slide, I am going to show you what is the importance of using a bromine versus iodine. You can see here we are clearly going to show you that if you use a bromine here, then you will end up getting to this corresponding bromonium, and then the BMR is going to open up the bromonium because these bromoniums are not stable. But if you have iodinium here, then you can see, okay, so it is going to get stabilized by forming this I3 minus here, okay. That is not possible in case of the bromonium, okay. So that's how this corresponding the iodinium intermediate will be stabilized. That will allow this 1,2 migration from the boron to the carbon to take place. So this is a olefin activation happening first. This is the iodine is coming to the double bond, forming a iodinium, getting stabilized, and this 1,2 migration is happening, okay. After that there will be elimination going to happen to form the corresponding product. So here what you are seeing, starting from this compound, once you treat this I2, it is going to go for this iodinium. You can see this reaction also, there will be base that can make this boron as a B minus, okay, and this can allow this 1,2 migration from this boron to the carbon, opening of the iodinium, and then you can see now there will be a trans or anti elimination. You can see there is iodine here, there is a boron here. So they are opposite to each other. They will be going to participate in a trans elimination to form this corresponding Z olefin. But that could be a E olefin if you can use a cyanogen bromide. Using that, what is going to happen? It is going to first form the bromonium, but the Cn minus can attack to the boron. Here you don't have a base, so it is going to form. Now this boron is going to become electron deficient. If you remember, I talked about the sodium cyanoborohydrates cases also. Now this X can give electron density to this boron and going to participate in a syn elimination. They can participate in a syn elimination to now it is going to form the corresponding E olefin. There are several examples of it. I am just going to show you some of the examples starting from this corresponding vinyl boron ester. If you treat the address lithium, okay, and then you can form this corresponding boron species. Now under the Zuiffel condition using the iodinium and the sodium methoxide, you can able to make corresponding Z olefin. It can be a syn elimination can be happen in this particular compound. Now if you can form the corresponding lithium here, and now if you use this, you can see in case of that you will be able to see the under the Zuiffel condition you will be able to get to this corresponding terminal olefin here. Again here you don't have the E and Z selectivity. The other example, you can take the this type of chiral boron compound vinyl lithium under Zuiffel condition, you can introduce terminal olefin. So this is another important thing that you can in this reaction you can also introduce terminal olefin by bringing a vinyl lithium. So if you have a chiral boron compound, you take a vinyl lithium that will form the boron 8 complex from here. So let's write down that if you have a chiral center, you have a boron here, B pin, then you are generating one vinyl boronate species. Okay. Now if you treat with the corresponding the Zuiffel condition, then this vinyl group will be transferred as you have seen. So now there will be not E and Z, but this vinyl group will be get into the attached with that chiral center. And then now if you can take the vinyl group, you can go for another round of the hydroboration oxidation, and you can able to synthesize the corresponding natural product. The other important reaction using organoboron compound is the Peter-Schiff reaction, and we are going to see that there 1,2 migration is still going to work here. So this is mostly a multi-component reaction, and you can see this reaction can be called a boronomanic reaction. So Peter-Schiff was discovered this reaction, the Nikos A. Peter-Schiff in 1993. After that this reaction became really famous. A lot of different example was done. Even a lot of this asymmetric and the diastoselective condition was developed. So this is a multi-component reaction because you can see there are 3 different compounds. One is aldehyde, one is amine, another is boronic acid to get to a secondary amine. So mechanistically there are different type of aldehyde. Aldehyde was developed. It could be sometime you will see that the aldehyde could have some other groups, like some other group attached here, which can be a which can act as a coordinating group. You can see it could be a OH, could be NH, some other things going to be here, which can act as a coordinating group to the boron. Sometimes it can work with simple aldehyde also. But mechanistically first going to happen, that if you have a amine and a carbonyl compound or aldehyde, it is going to form the corresponding imine, correct? So first thing it is going to form this one by attacking this nitrogen to the corresponding carbonyl group, and then the boronic acid you will form this OH, this oxygen can bind with the boronic acid, okay. And so there is 2 different type of mechanism written in the books. One could be you can go to directly to the imine, to the iminium. You can say it's after the OH, after the water from here. Once it lose the water, it will form the iminium, and you are forming this corresponding allyl boronate species. Sorry, the aryl boronate species. Now this can be transferred here through. So this aryl group is acting as very much as some sort of a nucleophile to act to the corresponding imine to get to this type of product. So this could be one type of mechanism. There is other type of mechanism which is mentioned, that in this particular time when you have a OH here that can bind with this the boron. So you can see this is a OH, so it's binding with the boron forming a B minus, and now this aryl group can participate. Aryl group can take part in a migration from this boron to this carbon, okay. So it can migrate from here to get and then cleave this carbon oxygen bond. So that is also mentioned in some cases. Again, there is some example. You can see synthesis of allylic amine can be done very easily. From there you can start with this corresponding amine and benzaldehyde, phenylvinyl boronic acid, the boronic acid, and you can get to the corresponding secondary amines. Okay, there are some other example to synthesize amino acid. Now the question I was telling you, that a lot of times you bring a carbonyl with a group like acid. So what is going to happen? Those acid group can or sometimes there will be OH group. They can act as a coordinating with the boron. Okay, so that can coordinate with the boron to form the corresponding boron species. So if you use the vinyl boronic acid, it will going to get to the corresponding. So now you are able to make to the corresponding tertiary amine, and as well as this is a amino acid because you have amine and the carboxylic acid. Yeah, first thing again I think you can see is formaldehyde dioxane. So this is synthesizing of a a marketed drugs, which the naftifine, okay, using a vinyl boronic acid. So it can get to the corresponding product with a very similar mechanism, and this chemistry was used for synthesis of further marketed drugs and bioactive compounds. Then here you can see there is an example of the synthesis of indole 3 carboxylic acid derivative by using the Petasys reaction. Here first thing is you can see the once you have this, so this carbonyl is very much activated because it is next to a carboxylic acid group which is pulling electron density. So aldehyde, so the indole, you have learned that indole is going to take a electrophile from the C3 position, add to the corresponding the carbonyl group first, forming this species which can abstract a proton, get to this corresponding indole. Now the boronic acid comes into the play. Okay, so the boronic acid can able to protonate this to get to this type of intermediate species. Now it is allowing this 1,2 migration to take place to neutralize this imine to get to this corresponding product. There are other examples for synthesis of bioactive compounds here. I think again you have this corresponding secondary amine, and you have this carbonyl with the corresponding acid, and you have the aryl boronic acid. So to get to this corresponding product which can be convert to the corresponding ester, which is this the clopidogrel. Okay, so that is the compound can be synthesized. Again, if you start with this corresponding chiral amine, now you can able to control the chirality of in the product. This chiral center will be remain intact. Okay, now what is going to happen here? You end up seeing this product. What is you end up this part going to be get introduced in the product, correct? So this is your starting material started with. This is the part got introduced. So now you can able to control. You can able to get to the 99% EE here. This is a mechanism. Again, I am just trying to show you the mechanism here, because what is thing happening here now? You are trying to do some sort of a dearomatization of this ring at the beginning to first the reaction to take place, very similar to the reaction with indoles. So this is the reaction with the corresponding carbonyl compound taking place, and then once you are going to rearomatize it, now the phenyl boronic acid is going to bind with the corresponding carboxylic acid. As I was telling you that if you have a carboxylic acid, the boronic acid is going to bind with it from the boronate complex, and now you can see that this OH at the same time it can also protonate this OH to a H2O. This nitrogen can pull the electron density, dearomatized, and form this sort of intermediate where the phenyl group can transfer from boron to this particular carbon here to get to this product. Okay, this is a very interesting transformation. You can see starting from this compound, you are literally introducing this entire group in the para position. There are more examples for synthesis of the biological active compounds. Again, you can see in this particular example, you can clearly see here that you have this amine here. There is a primary amine here which is reacting with this compound under the Petasys condition to get to this corresponding product. You can see this is again there are some more example here. You have this boronic acid, you have this the corresponding aldehyde with the carboxylic acid, you have corresponding diamine here, and you can see here what is happening. First there is a the Petasys reaction. First there is a I think the coupling of this NH with this corresponding in the intermediate which is forming here. Okay, and then there is a Petasys reaction happening first in this part, and then what is happening now? You have the next NH can able to react with this corresponding so you can see now I think there is a coupling between this amine and acid which is catalyzing by the boric acid. So, boric acid catalyzed this amide coupling reaction to get to this product. Okay, very similar thing happening here as well. First there is a petasis reaction, then there is a amide coupling. Again, in some cases there is a I think if you have this particular compound here with you have a chiral center here. As I was telling you, you can do this reaction with a hydroxy group also, which can also be kind of directing some of these transformations. So now if you have that scenario, there is two different cases can happen, type of tangent state can be happening. It could be this one or this one, and this is more favor versus this. Because first thing, if you remember, you have this primary amine here, it is going to form this iminium here, and now based on this iminium geometry, you can think about if you think about this as like a double bond, then there is this 1,3 allylic strain here can be make an important role here for which can be avoided in this particular tangent state to get to the corresponding. So you can see a corresponding anti product is forming as a major product instead of this corresponding syn product to avoid the corresponding A13 allylic strain. So in this part I talk about I think the 1,2 migration chemistry. You have learned about the G fuel or olefination, and then I talk about the petasis reaction, the multi-component reaction, which is a Bohr-Nuttig reaction. Again, these are the references, and again, thank you so much for coming to the class. I'm going to see you guys in the next class.